now that we have talked about the physicochemical nature of the double bond, so it consists of a sigma bond and a pi bond, we can ask ourselves which substituent patterns at a double bond are the most stable ones. And you remember the carbon-carbon atom has, of course, 4 free places for a substituent, and you can put the substituents in different ranges. So, for example, both of them at one carbon atom or at different ones. And we discussed in the introduction or in our recap, the different E and Z isomers that also play a role here. And I would like you to think about for a moment about the stability of these substitution patterns, and maybe you can come up with like a line of conclusion which substitution pattern is maybe favored or more stable compared to others. And pause the video if you want to think about that for a moment. And then if you come up with the solution, we can now discuss this. There are 2 aspects that are important for the stability of the alkenes, and that is first the sterics. And that's something that we can easily see when we look at the 3 different substitution patterns when we have 2 moieties at our alkene. And here we have the pattern for the E substituted alkene, the Z substituted alkene, and the terminal disubstituted alkene. And what you can see here is, as when these 2 moieties are on the same side of the molecule, either attached to the same carbon atom or in this Z configuration, that they are also on the same side of the carbon one, they are roughly equal in stability. Of course, depends a little bit on what moieties you have here in the end, but they are more or less same. But what is more stable than these 2 substitution patterns is the E substitution pattern, because the 2 moieties avoid each other, so the steric strain on this molecule is then reduced. And this favors overall this E or trans substitution pattern. And on top of that, what is also important, apart from the sterics of these ligands, is the electronics. And here we can come to the conclusion that the more substituents we have attached, the more stable our alkene is. In general speaking, of course, you can always find exceptions from this rule. But in general, these tetra-substituted alkenes are the most stable ones, because the organic moieties here at both sides of the double bond stabilize the double bond quite well. And if we have like a terminal double bond, so only mono-substituted alkene, then it's the least stable. And this, of course, is then least stable, means also highest reactivity towards certain reactivities. And another thing that's important, apart from the sterics and electronics, as we've discussed, is the so-called hyperconjugation. And as you remember from the introduction to chemistry, this is basically the transfer or the stabilization or the stabilizing influence of a neighboring orbital, or a neighboring CH sigma orbital here, and this can stabilize this. This double bond here that is made up of this pi bond, and especially here the pi star orbital. And this is especially important for these so-called allyl fragments, where when you, for example, deprotonate here adjacent to one of these double bonds, then you get a negative charge, so you get a carb anion. And this carb anion is now stabilized because the resulting p orbital that's formed in the direct vicinity to the double bond can now conjugate with the pi bond, and so the electron density is delocalized through these 3 carbon atoms, where previously it was only localized at 1 carbon atom. And this is then less stable, as when the negative charge is delocalized across 3 carbon atoms. Okay, that was it for the stability of the alkenes and the physical chemistry nature. And next we're going to have a look at the addition reactions.